Hello everyone, this is the second lecture in real analysis. The topic of this lecture is axioms of real numbers. In particular, we are going to discuss ordered field axioms. So the definition of a field has been given in the previous video, which is linked down in the description of this video. So you can watch the previous video if you want to find out what is a field. In this video, we are going to define an ordered field. And we are going to state and prove some properties of ordered fields. And the reason why we talk about ordered fields is because the set of real numbers is an ordered field. So we want to understand what that means, and therefore we are going to discuss what is an ordered field. So before we proceed, let us recall what is a field. So this is the definition of the field that we have given in the previous video. So field is a non-empty set with operations of addition and multiplication that satisfy these 7 axioms: commutativity, associativity, existence of additive identity, existence of additive inverse, existence of multiplicative identity, existence of multiplicative inverse, and distributivity. So in this video, we are going to refer to these axioms as field axiom 1, field axiom 2, and so on, field axiom 7. Let us also recall the theorem that we stated in the previous video, which states further properties of a field. So if we have a field, then the following 8 properties hold in this field. I'm not going to read them out loud. We have discussed them before. Like for example, 0 times a is equal to 0, minus -1 times a is negative a, and so on and so forth. So there are 8 properties of the field which we are going to use in this video. So our next goal is to define an ordered field. So in order to be able to do that, we need to recall what is a relation. So R is a relation on a set F, that is a non-empty set, if R is a subset of the Cartesian product of F with itself. And just to recall, Cartesian product of F with itself is just a set of all ordered pairs AB, such that A is in F and B is in F. So a relation is simply a set of ordered pairs such that each element in the ordered pair is an element of F. So for example, the operation of comparing rational numbers is a relation. So we say that the ordered pair AB is in this relation R if A is less than B. So our next example is to basically introduce the ordering on a field F. So let F be a field, and suppose we have a relation R on the field F. So we are going to write A is less than B if AB is in R. We are going to write A is greater than B if BA is in R. We are going to write A is less than or equal to B if A is less than B or A is equal to B. And we are going to write A is greater than or equal to B if A is larger than B or A is equal to B. So, so far, this relation R is not necessarily an order, right? So R must satisfy some properties in order to introduce an order on the set F. So R must satisfy certain properties to be an order on the field F. So here is the definition of an ordered field. So an ordered field F is a field together with a relation R on it, satisfying the following axioms. So the first axiom, which we denote by ordered field axiom 1, is the trichotomy. So for every two elements A, B in F, exactly one of the following is true. Either A is greater than B, or A is less than B, or A is equal to B. So trichotomy stands because there are three options in here, so that's why we call it trichotomy. The next field axiom is transitivity. So for every three elements A, B, C in F, if A is less than B and B is less than C, then A is less than C. The next axiom is called additivity. So if we have three elements A, B, and C in F, and if A is less than B, then A plus C is less than B plus C. So we can basically add C to the inequality. And the last axiom is multiplicativity. So if we have three elements A, B, C in F, and if A is less than B and C is greater than 0, then AC is less than BC. So we may recall from the properties of real numbers is that if we multiply an inequality by a positive number, the inequality doesn't change. So this is basically what we remember about real numbers. We can recall what we stated before, and what we stated before is that R is an ordered field, and it is an axiom, so we are not going to prove this. And now we really understand what that means. So the fact that R is an ordered field means that these four axioms are true on R. And remember, R is a field, so the 7 axioms of the field are also true on R. So we are amassing more and more axioms for R. So you may say that you can state many more properties of inequalities for the real numbers. So how come all of those properties are not reflected in the ordered field axioms? This is because from the axioms of the ordered field, we can derive many more properties. So here is a theorem. So let F be an ordered field. Then for all elements A, B, and C in F, the following 8 properties are true. So if A is greater than 0, then minus A is less than 0. And also if A is less than 0, then minus A is greater than 0. The second property is that if A is less than B, then minus A is larger than minus B. Also, if A is larger than B, then minus A is less than minus B. So we basically have to change the sign of the inequality if we multiply it by -1. The next property is that if A is less than B and C is less than 0, then AC is larger than BC. Also, if A is larger than B and C is less than 0, then AC is less than BC. So if we multiply an inequality by a negative number, we have to change the sign of the inequality. The next property is that 0 is less than 1. So remember, 0 is the additive identity and 1 is the multiplicative identity. So it's important to establish how they are ordered. The next property is that if A is greater than 0 and B is greater than 0, then A is less than B if and only if A squared is less than B squared, where A squared is A times A. The next property is that A squared is greater than or equal to 0. The next property is that if A is greater than 0, then the multiplicative inverse of A is also greater than 0. And the last property is AB is less than A squared plus B squared over 2. So now we are going to prove some of the statements in this theorem, and we are going to have to use the axioms of the field, the axioms of the ordered field, and some properties of the field. So for this purpose, let us say that this is theorem 2, and theorem 1 is going to be the theorem with the properties of a field, which we stated in the previous video. So just for us to be able to refer to that theorem, let us say that this was theorem 1, and the theorem that we are stating right now is theorem 2. So let us begin with this proof of the statement I of theorem 2. So let A be an element in F such that A is greater than 0. What we want to show is that negative A is less than 0. That's what statement I is. Statement I says that if A is greater than 0, then minus A is less than 0. So that's what we are going to aim to show. Let us note that we can only use the field axioms. So there are 7 field axioms, which we denote by field axiom 1 through field axiom 7. We can use the ordered field axioms, ordered field axiom 1 through ordered field axiom 4. And we can use the statement I through 8 of theorem 1. So this is what we have at our disposal. Using all of these properties of an ordered field, we want to show that negative A is less than 0. So let us begin with the trichotomy. So by trichotomy, one of the 3 options holds. So either negative A is equal to 0, or negative A is greater than 0, or negative A is less than 0. So our strategy is going to be to show that this is not true, show that negative A is not equal to 0, and we want to show that negative A is not positive, and therefore by trichotomy the only option that is going to be left is that negative A is less than 0. So that's going to be our strategy. So case 1, negative A is equal to 0. So this implies that negative 1 times A is equal to 0. And this is by theorem 1. Right? In theorem 1, we stated that the additive inverse of A is the same as negative 1 times A. So this implies that negative 1 times A is equal to 0. So, but in theorem 1, we also stated that if the product of 2 elements of the field is equal to 0, then one of them should be equal to 0. At least one of them should be equal to 0. So then either negative 1 is equal to 0, or A is equal to 0. So if negative 1 is equal to 0, then minus 1 is equal to minus 0. However, the additive inverse of 0 is equal to 0. And then by theorem 1, the minus of minus 1 is 1. So then 1 is equal to 0. However, by the field axiom, that is the existence of multiplicative identity, 1 is not equal to 0. But 1 is not equal to 0. So that's a contradiction. So hence, negative 1 equals to 0 is not true. Right? Because we assume that negative 1 is equal to 0, we arrived at a contradiction. So therefore, negative 1 is not equal to 0. So we had that -1 was equal to 0 or a is equal to 0. So therefore we must have, so hence a is equal to 0. However, if a is greater than 0, but a is greater than 0, so that's a contradiction. So from our assumption that -a is equal to 0, we arrived at a contradiction. We arrived at a equals to 0, but a is larger than 0, and that's a contradiction. So hence minus a equals to 0 is not true. So minus a is not equal to 0. Okay, so case 2, minus a is greater than 0. So we also have that a is greater than 0. So by ordered field axiom 4, which is multiplicativity, we have that minus a times a is greater than 0. So we can just take this inequality minus a greater than 0 and multiply it by a, which is positive. So then we have minus a times a is greater than 0. We have minus a squared is greater than 0. Now you may say that's already a contradiction. Well, we haven't really shown that a squared is greater than or equal to 0. So we cannot use that yet. So on the other hand, if we take the inequality a greater than 0 and multiply it by a, we are going to get that a times a is greater than 0, which means a squared is greater than 0. So then we are going to have to come up with some kind of contradiction. So let us look at this chain. So 0 is the same as 0 times a, and this is true by theorem 1. So if we multiply a by 0, we are going to get 0. So 0 is 0 times a, which is the same as a plus minus a times a, right? Because a plus minus a is equal to 0. So instead of 0, we now have a plus minus a. And then by distributivity, this is a times a minus a times a. So this is a squared plus negative a squared. So a squared is greater than 0. So this is greater than 0 plus minus a squared, which is minus a squared. But minus a squared is also greater than 0. We just showed that. So minus a squared is greater than 0. So in the end, what we showed is that 0 is greater than 0. So we showed, so in the beginning of this chain, we have 0, and at the end of this chain, we have 0, and the inequality between them is greater than. So we showed that 0 is greater than 0, but 0 is equal to 0. So by trichotomy, we cannot have both of them. We can only have one of them. So this is a contradiction. So case 2, negative a greater than 0 is not true. So by trichotomy, we now must have that negative a is less than 0. So hence by trichotomy, negative a is less than 0. We eliminated the other two possibilities, so negative a is less than 0. So that's the proof of the first portion of the first statement of the theorem. So as a homework, you can prove that if a is less than 0, then minus a is greater than 0. So the proof is going to be very similar. We are not going to prove all of the other statements of theorem 2. This is again left as an exercise in case you want to do that. We proved this statement I, actually the first portion of the statement I, just to show you the flavor of how these kind of proofs go. So instead we are going to discuss a few more properties of the ordered field. So let F be an ordered field, and let A be an element in the ordered field. Then absolute value of A is defined to be equal to A if A is greater than or equal to 0, and negative A if A is less than 0. And so the following theorem is true. These are the properties of absolute values. So let F be an ordered field. Then for every two elements A and B in F, absolute value of A is greater than or equal to 0. Absolute value of A is less than B if and only if A is in between negative B and B. Absolute value of A is larger than B if and only if A is less than negative B or A is larger than B. Absolute value of the product AB is absolute value of A times absolute value of B. Absolute value of A plus B is less than or equal to absolute value of A plus absolute value of B. So this one is called the triangle inequality. And finally, absolute value of A minus absolute value of B is less than or equal to absolute value of A minus B. So we are not going to prove this theorem. However, we are going to discuss some intuitive understanding of this theorem. So in case F is the set of all real numbers, it is convenient to think about the absolute value as the distance from A to 0. So absolute value of A is the distance from A to 0. If we depict the real line like this, and if this is 0, and A is here, then absolute value of A is distance from A to 0. So for example, if we take a point B over here, so in this case B is negative, so then the absolute value of B is the distance from B to 0. And so we can illustrate the statement II as follows. So suppose we have a 0 here and the real line. And suppose that B is here. And we have that the absolute value of A is less than B. So that means that the distance from A to 0 is less than B. So the distance from A to 0 is less than B. So A could be here, right? The distance from A to 0 here is less than B. However, if we have negative B in here, this distance over here is also B. And so A could be any of these points. So absolute value of A is less than B if and only if A is in the interval negative B to B. So which is the same as to say A is between minus B and B. So this is how we illustrate statement II. So this is all for this video. Thank you for watching it. Put a like underneath this video if you like it. Subscribe to this channel. In the next video, we are going to talk about the completeness axiom of the real numbers. So I hope to connect with you in the next video. And for now, bye and be good at math.